Good afternoon and good morning. Welcome to the third session of Theme 1 in the IWRA online conference, Groundwater Natural Resources Assessment under Climate Change. My name is Richard Taylor and I'm based at University College London in the UK. And I will be your chair this morning and this afternoon, depending on where you are. And my co-chair is Sara Nowreen, who's an assistant professor at the Bangladesh University of Engineering and Technology in Dhaka, Bangladesh. We'll now begin this morning's session, and I'll now ask Sara to introduce the first speaker.
Thank you, Richard. This is Sara. I want to introduce the presenter to start our today's session. The theme of today's the theme is the groundwater natural resource assessment under climate change, of course. And our first presenter, if Richard allowed me to tell his details, that's John Mackay. He's a hydrologist of British Geological Survey, doing mainly the hydrological process modeling of land surface and subsurface. And he's going to present his presentations on Proglacial groundwater storage dynamics under climate change and glacial retreat. So over to you, Jonathan, if that's okay.
Thanks, Sara. Thanks, Richard. Yeah, so I'm going to talk about proglacial groundwater storage dynamics under climate change and glacier retreat. So I thought we'd kick it off with some glaciers and groundwater to make it interesting. So next slide, please. So proglacial groundwater systems. So what are we talking about here? So this could be anything from sort of overburden materials, things like talus piles and moraines that you find in glacial environments, or it could be larger alluvial aquifers that you find in the valley bottoms and the sort of mountain front systems like the Sander that you can see in the top right hand corner there. That's a large outwash floodplain in Iceland. That's actually going to be the focus of this talk today. Or it could be things like mountain wetlands that you find in valleys, mountain valleys in the Andes, which you can see in the bottom right hand corner there. So these are remote systems. They are rarely studied, therefore, but increasingly we think they play an important role in mountain water cycling and particularly downstream water provision. So they very much feed into this narrative of climate change, glacier retreat and water scarcity that we're seeing a lot in the literature at the moment and in the news. I've also just put there a point that there's been quite a lot of work in the ecology in riverine environments, in glacial environments, and groundwater is known to be an important regulator of ecology. It provides nutrients and very much controls the physiochemical properties of surface water systems in these otherwise quite harsh environments. Next slide, please. So the focus of this study is the Virkisjökull Glacier Observatory. This is in southern Iceland. Virkisjökull, you can see on the left, there's a big glacier that then feeds the Virkisa River, which emanates along the south. It flows over this large outwash floodplain, this big alluvial aquifer. Again, you can see in the top right-hand corner there. This is up to a couple of 100 meters thick, unconsolidated, unconfined, made up of all the sediment that's been kicked up the mountains over the years. And then we can see a kind of conceptual model in the bottom right-hand corner. So if we can go to the next slide, please. Great. So you can see those two graphs there, and this is quite characteristic of glacial environments. You get the runoff seasonality coming from the glacier, so it's very much melt driven, which peaks in the warmer months, in the summer months in this region. That then flows over land and then infiltrates into the sander, so it provides a source of recharge. But then you get this contrasting seasonality of the diffuse recharge signal, which typically peaks in the winter, autumn, spring months. So you get these two kind of dynamic inputs to the groundwater system, which can bring about quite interesting groundwater dynamics in the sander. So next slide, please. So as I said, these are quite poorly studied systems. So we had two main research questions we wanted to answer. Firstly, what drives the proglacial groundwater storage dynamics in the system. So is it the glacier or is it diffuse recharge from the regional climate? And secondly, how might proglacial groundwater storage dynamics respond to 21st century climate change and glacier retreat? So next slide, please. So how do we do it? This is a methodology. I'm not going to go into lots of detail about this because there's a lot of detail here, but essentially we used an integrated climate glacier groundwater model. So we had a glacier hydrological model. You can see in the bottom right-hand corner here, which basically simulates glacier dynamics and meltwater runoff. And then we have that driving a distributed groundwater model, a mod flow model of the sander. So basically the glacier hydro model provides boundary conditions. It provides the meltwater runoff input at the top of the mod flow model. And it's a wider hydrological model. So it provides diffuse recharge, so the infiltration into the subsurface to the water table. And we had lots of different potential scenarios we could drive this integrated model with. We actually had up to about 90,000 different runoff and climate combinations, and that's from some previous work we've done where we've been experimenting with the glacier hydrological model. So we whittled that down just to five scenarios, and we used cluster analysis to do that, so choose 5 distinct scenarios to drive our groundwater model with. And those scenarios are made up of different temperature changes, different changes in glacier retreat, different meltwater runoff inputs from the glacier, and different precipitation inputs over the sander. So they try and take into account these kind of different combinations of characteristics that will drive changes in groundwater dynamics in the sander. So next slide, please. So on some findings, so I'm going to show you a few graphs and plots that look like this, lots of squiggly lines. These are essentially 30-day moving average outputs from the groundwater model, and they're averaged over the years, so we can basically see the seasonality of different variables. So the black dashed line is the control simulation, which is the historical simulation, 1980 to 2010, and then the 5 colored lines are the different scenarios that we drove the model with, and these focus on the 2080s, so right at the end of the 21st century. We wanted to do that just to kind of highlight the change. So the first one, figure A, is looking at groundwater seasonality, and we saw that it can change to a certain extent. You can see some of them, you see quite sort of flattening of the hydrograph, and some of them you can see shifts in timing of the min and max. So we do see some sensitivity, certainly, to climate change and to glacier retreat. But then when we looked at the diffuse recharge, which is shown in B for the different scenarios, and particularly C and D, which show the changes in groundwater level and the changes in diffuse recharge, we found that these actually quite closely correspond to each other. So a first indication that probably groundwater dynamics in this system are driven by the diffuse recharge signal rather than the meltwater runoff signal coming from the glacier. But we can go on to the next slide, please. So then we looked at base flow dynamics, and again, there's lots of information here. I'm not going to go into lots of detail, but yeah, we looked at the base flow inputs, and as we groundwater level, base flow is projected to fall on average. So if you look at figure D there, the bottom left-hand corner, you can see the base flow signal actually looks very similar to the changing groundwater level signal that we found before. So an indication that base flow is very much controlled by groundwater dynamics, which are then controlled by diffuse recharge. So again, we're seeing the sort of dominant control of diffuse recharge rather than the glacier on the system. But importantly, we found that groundwater contributes up to about 15% of runoff. So if you look at figure B there, the middle top one, you can see groundwater contributes up to about 15% in the cooler months of the year when there's not as much meltwater input. So it is a significant contributor to this glacial river. And then that's projected to fall in the future. So we were kind of thinking it might rise actually as you're getting a reduction in meltwater inputs, but the reduced contribution is due to actually an increase in meltwater inputs in the cooler winter months. So we're seeing that obviously in the winter months, the temperature's rising, and that is therefore increasing the amount of melt into the system. So it's not necessarily the groundwater's contributing less, but it's the glacier meltwater is actually contributing more in the cooler months. So next slide, please. The final thing we looked at was river recharge dynamics. So if we look at figure A here, you can see that contrasting seasonality. We can see the peak in river recharge in the warmer summer months of the year. So it's highest during the melt season. And we found that it contributes up to about 39% of total recharge, depending on which month of the year you're looking at. So it can be a really significant input, and it actually contributes about 15% on average of the total recharge to this groundwater catchment. So the glacier is essentially an important contributor to the overall recharge of this system, which was really, really nice to see. The seasonality of changes, they pretty much follow the length of losing river. So we can see, if we look at figure C here, we can see that river recharge is projected to increase, particularly in the winter months when groundwater levels are predicted to fall. And that's essentially due to the length of losing river, which is projected to increase as well. And you can see that in figure B here. But there's one anomaly here, which is that yellow scenario. So if you look at figure C, you can see that yellow line was a massive reduction in river recharge in the summer months. And that's not because of a big reduction in length of losing river. So it's nothing to do with the groundwater. There's actually something going on with the recharge mechanisms here. So you can go on to the next slide, please. So we looked more closely at the river stage hydrograph for these different scenarios. And this is looking over the control period. You can see a period of 3 days. And you can see the diurnal variation in figure A of river stage. And that's basically because of the daily melt cycle in the river. And it's actually this diurnal variation that drives the head gradients. Sorry, I'm very close to finishing, so I'm pretty much on my final slide. It's that diurnal variability that drives the head gradient at the river aquifer interface. And if you look at figure C, it's that diurnal variability that drives river channel infiltration. And it's the glacier retreat and the subsequent loss of that diurnal variability in the hydrograph that causes that reduction in river recharge. So we're seeing here for the first time a mechanism by which glacier retreat could inhibit and could make proglacial groundwater systems vulnerable to climate change. So final slide, please, and I'll just conclude. So conclusions, the Verkisa River, we found the river to be an important source of proglacial groundwater recharge. So the glacier is an important source of recharge. And we showed a mechanism for the first time, a mechanism by which glacier retreat could inhibit this recharge. We found that groundwater storage dynamics are generally resilient to changes in this river recharge in this system, because it's a temperate system, it's a very wet system, but in more arid environments, we'd probably find they're more susceptible to climate change, more vulnerable to climate change. And finally, groundwater will continue to buffer proglacial river runoff. So groundwater is an important contributor to the overall provision of downstream water. Yes, thank you. Sorry for overrunning slightly.
Thanks, John. We are running out of time, so further, talking about the questions, we will try to answer them at the end of the sessions, at end of the at the end of our sessions by the panelists, of course. So now I want to present. I want to request the second presenter, Gong. She's an early career researcher, now doing her PhD at the School of Geography and Planning at Sun Yat-sen University, if I say it correctly, pronounce it correctly, sorry. Her presentations is on propagation from meteorological to groundwater drought response to global warming.
Thank you, Richard and Sara. Thanks, organization, for this opportunity to give my presentation. Good morning, everyone. Today, my topic is propagation from meteorological to groundwater drought response to global warming. I'm from China, Yangsan University. So next slide, please. Many footprints shows widespread increase in air temperature. Natural change from our Earth lead the temperature up and down, such as Nino phenomenon and so on. ISCO also give the other evidence. Increase atmospheric carbon dioxide. Natural force burning is still the main cause. In the ecosystem, human also contributed a small part of the rise, including failure. So climate change is our research background. Next slide, please. Yesterday, many professors and researchers presentation mentioned the observed impacts under climate change. The more intense rainfall events, higher evapotranspiration surface line on the groundwater recharge change. Professor Richard proved it using piezometric and isotopic evidence, and many local measured evidence from researchers. Response to global warming, the more intense rainfall events and the higher evapotranspiration have impact on surface water drought. Drought propagates through the hydrological system and may affect groundwater resources by reduced recharge. Although displaying better adaptation to drought crisis, groundwater use abstracted, approaching, or exceeding recharge will also increase the severity and the magnitude of surface water underground water drought, which fully expand water recycling ecosystem. Next, please. Okay, understanding the propagation from meteorological to groundwater drought is important for the early warming of the groundwater drought. This presentation investigates drought propagation in a custom area, later Peninsula, China, focus on propagation process from meteorological to groundwater drought. Drought events include development and the recovery process. Extra drought characteristics by running theory. D is the number of the drought months. M is the cumulative defect during the drought. D. Pi is the minimum absolute value of the drought index during the day. BD, the bridge drought is the drought event. So the DDD is the drought development during from the time of the start of the drought development to the end of the drought development. The DRD is the drought recovery duration from the time of the start of the drought recovery to the time of the end of drought recovery. TL is the transaction level of the ROM theory. The ROM theory has been widely applied to identify drought characteristics during its advantages, such as having a simple principle, the convenience of the describing the drought propagation from the beginning to end, and the ability to extract multiple drought characteristics from the drought index series. Recognizing drought development and the recovery time can give us total occurrence time. Sleep and the time length can reflect the severity. The air shows the frequency. Next, please. Standard propagation index was used to analyze the number of the under the severity of the meteorological drought. Under the propagation in the groundwater aquifer was investigated by analyzing groundwater drought index with the threshold level method. Compared with meteorological and groundwater drought index, propagation time through hydrological system can be shown, which provides support to analyze the drought propagation process. Results indicated that the drought was weakened when propagation to groundwater, and the frequency also decreased in groundwater drought. Next, please, was in this slide. Thank you. The propagation time from a meteorological to groundwater drought had different performers in shallow, middle, and deep aquifer. Reasons: maybe the slow groundwater cycle. Some researchers used the change rate of the water storage defected to present the recovery speed during the duration of the drought to confirm the recovery time rather than the recovery period alone. The drought development duration is often overlooked. However, the drought the drought propagation speed of drought is variable rather than uniform speed because the groundwater drought propagation is affected by many influencing factors, such as groundwater recharge and discharge, human activities. When drought appears, continuous decline of groundwater will occur. Next, please. Correlation analyzed between maximum and the average temperature on the drought index define the causes of the drought. Using the time series of measured groundwater table on the presentation, groundwater drought events occurred with continuous greater than 3 months meteorological drought. However, not all meteorological droughts lead to groundwater drought. Groundwater is a vital resources. Studying on the groundwater drought, studies on drought position and global warming are important for future fresh supply. Next step, I will focus on hydrological drought, which makes clear process from the meteorological drought to hydrological drought and to groundwater drought. Next. Thank you for your listening. Please feel free to ask me if you have any question.
Thank you, Gong, for your presentation. That was great. We are running a little on time, so as I said, we will take questions in the plenary. We'll continue to our next speaker, and I'll ask my co-chair, Sara and Nowreen, to introduce the next speaker.
Thank you, Richard. Our next presenter is Alan Ricardo Patlan Hernandez, if I pronounced it correctly. He's an in epidemiology studies officer in the Action Center law firm of France. He is basically a medical doctor currently studying master's specialized of public health and infection risks in France. Alan is presenting the presentations. It's about investigate the relationship between hydro-climatic monitoring and health indicators in a context of chronic drought.
Hello, everyone. Thank you for joining us in our session today. So today I will present you a research project that it's combining, or it's a collaboration between the humanitarian, public health, and hydrosciences fields. As Sara already told you, I work for Action Against Hunger France as an epidemiologist, and Action Against Hunger, as well as many other organizations around the world, is concerned right now about the impacts of climate variability after climate change on populations' health, especially when it comes to the most vulnerable ones. Next, please. Okay. So if we talk about vulnerable populations, we can go to the southwest Madagascar, where the population is already facing important economic and social issues, as well as additional negative impacts of climate variability on nutritional status and population's health. So despite these observed negative impacts of climate change or climate variability, not only in Madagascar, but in many other zones around the world, the climate monitoring is still not enough, and the evidence that we produced so far is not enough to allow us to fully understand the relationship that there is between acute malnutrition in this case, other health indicators, and the climate variability. Next. Please. So this is why our project aims to assess the relationship of hydro-climatic monitoring data with nutritional and morbidity indicators in the district of BUET specifically, in order to identify which are the hydro-climatic indicators that have an association with nutritional and morbidity indicators and describe the significant temporal associations. One click more. And next slide, please. So for this, we conducted a retrospective observational study based on hydroclimatic and nutritional data from the district of BUET in Madagascar from January 2014 to March 2019. our hydroclimatic variables were the monthly pluviometry, the monthly piezometric index, as well as the monthly leaf area index. And our nutritional status variables were represented by the number of admissions to the centers for outpatient rehabilitation for severe malnutrition, and the number of screened children with acute malnutrition. Next slide, please. So to assess this relationship, we started first with regression models and cross-correlation functions. It's important to say that this was only a preliminary and exploratory analysis with the data we had available, and we are now currently going further with the analysis using more specific or adapted methods to our data series. Next, please. So as the preliminary results in the next graphics, we can see in the graphic, or we can observe in the graphic at the top, the monthly cumulative rainfall for this district. In the middle, we can see the monthly piezometric index, and after at the bottom, we can see the monthly admissions to malnutrition treatment centers. As we can clearly observe in those graphics, the hydroclimatic indicators follow a seasonal pattern, which is expected in different regions. But also we can see that there exists an interannual variability that it happens to be very, we can see very clear from one year to another. Maybe we can see that in some years the rainfall season is stronger than in other. And so on. So if we see the graphics and we only think in those indicators as having only a linear relationship, we could thought that each indicator, or in the graphics, the cases of malnutrition are related with the increases of hydroclimatic indicators, right? So we can see that the increases in the admissions due to malnutrition are rising at the same time as the hydroclimatic indicators. However, this wouldn't be consistent with the field, with the observations that we have on the field, nor with the existing literature that already describes the relationship between stunting, that is chronic acute malnutrition, with some hydroclimatic indicators, as well as with other literature describing the impact of climate change on other diseases. However, there are some effects of climate change that haven't been explored so far. And so we hypothesize that there is a plausible lag association between the hydroclimatic variables and the acute malnutrition occurrence in the first stage. And also there is a lagged impact of hydroclimatic variability with other health indicators that we are going to test. Next slide, please. So for this, we use a cross-correlation function that allows us to assess this plausible temporal correlation I talked about. In the preliminary analysis with the available data, we observed that significant increases in the number of admissions due to malnutrition are correlated with the decreases in the piezometric index, and these increases are in the admissions due to malnutrition comes 2 months after the piezometric index decreases in the district of Etioquia, as we can see in the graphic on the right. Next, please. So to our knowledge, this would be the first study aiming to assess and characterize the impacts of climate change on acute malnutrition. It's important to say that in southern Madagascar. These preliminary results, as I told you, are part of a wider study for which we will perform more robust analysis, including other factors, as I told you also, not only malnutrition, but other factors that might play an important role in the pathway to malnutrition, but also factors or diseases that can be impacted by climate variability. That is to say, specifically the diseases that we know as climate-sensitive diseases. These preliminary results are consistent also with previous evidence of lagged impacts of climate on health indicators. There are some literature describing, for example, impacts of climate variability, on dengue, etc. And each time more and more the scientific community is choosing to use or to measure the impact of climate change, but also to use hydro-climatic indicators to model the behavior of some diseases. So that is very important. So how is this addressing groundwater resilience? Well, the continuity of this project needs research component is very important because it will help us to enhance the groundwater monitoring and the public health surveillance in this zone that is facing chronic droughts and where the surface, where the water surface resources are almost inexistent. It will also improve the forecasting of the health indicators through the hydro-climatic surveillance in southwestern Madagascar with potential replicability in similar humanitarian context that is very important for associations as Action Against Hunger and other field actors. Next slide, please. So based in the available data that we had at the moment, we could identify that there is this significant association between the hydro-climatic indicators and the prevalence of acute malnutrition. We are going further with other health indicators, but for the moment we identified that, and most importantly, we could identify also that these are lagged associations, not only, and they not follow only a linear relationship. So to explore the next indicators and to explore more this association, we will perform more robust analysis, including the indicators on climate-sensitive diseases, as I mentioned, and complementary hydro-climatic and nutritional indicators, not only this time from BUET, but from the 8 districts in southwestern Madagascar that are currently facing the same situation in droughts. So thank you very much.
Yeah, thank you very much for your presentation, Alan. Very interesting. We don't have time to take a question right now, but I'm going to pose a question to you right now that we'll answer in the plenary. And that would be if you could explain in the plenary the conceptual model that you have that is linking these hydroclimatic variables to that observed malnutrition. It wasn't as clear. If you could provide a conceptual model that joined the dots between the hydroclimatic variables and the malnutrition. We'll do that in the plenary though. Sara, could you please introduce the next speaker?
Okay, our next presenter is another early career scientist who is doing his PhD in University of Minho, that's Nasser Tuqan, and he is basically from Portugal. He's going to present his presentation today on agricultural water use impact on the Eastern Aquifer Basin, which is actually based in the state of Palestine, about sustainability under climate change uncertainties. Tuqan, here you go.
Thank you, Dr. Nowreen. Thank you, Professor Taylor. Good morning and good afternoon, everyone, regardless of your time zone. I would like, as Dr. Nowreen explained, I would like to present the agricultural impact on the Eastern Aquifer Basin, which is one of the main aquifer basins in Palestine. Next slide, please. And when you mention Palestine, generally speaking, one of the first things that probably come to your mind as perception is the conflict between both sides, Israel and Palestinians. And one of the long-standing issues on the peace negotiations between both parties is water. And when you mention water with the Palestinians, that's 95% of our water resources, basically groundwater. For the aquifer basin system that we have, which combined 4 different aquifers, the one that takes most of the area within the Palestinian territories is the Eastern Aquifer Basin, roughly 50% of the West Bank's total area, which means more or less 47% of the Palestinian total lands. And in 2011, the overall withdrawal was around 50 million cubic meter by the Israelis, 42 million meters by the Palestinian. That sounds good when you look in the long-term recharge, but as we're going to see later on, probably those numbers are not pretty accurate. It has long been very important in terms of economy and agriculture. For instance, 60% of all Palestinian vegetables are produced there. And also in terms of the economic value, it's the location where most of the Jordan Valley, Palestinian part of the Jordan Valley is located. And that has lots of impacts also on the economy and the tourism. That's why 90% of most of the water abstracted from that aquifer goes into that area. Next slide, please. So what we did is basically we wanted to assess the agriculture, because agriculture is the main water user in that area. We wanted to assess the impact considering climate change on the aquifer. We adopted sufficiency. I'm going to explain the next slide about sufficiency as the main assessment approach. For sufficiency, it requires quantity, quality data in addition to socioeconomic data. And to do that, we needed to perform wide-scale data collection from official records, Palestinian official records, survey lots of farmers in that region. In addition to that, we interviewed the head of water resource, the Palestinian Water Association, and also we needed a credible source of climate change information. Next slide, please. When it comes to sufficiency, which is a very powerful method, in my opinion, about assessment of water use, it is based basically on water balance. It accounts for every single water flow coming into a system or going out of the system. And it considers 3 dimensions of each water flow: quantity, quality, in addition to beneficence. And that's why you can also see the efficiency assessment from different perspectives: farmers' perspective, managers' perspective, which we've done. In addition to that, sufficiency assesses the efficiency of water use on 3 different levels or scales: macro, meso, and micro. For micro, it's a local level within the water use system that you define, while for macro, it's more on the water source itself, the aquifer itself, which means transboundary typical type of analysis, while meso is somehow in between the impact of a system itself within the water use system on the actual resource. And that's what we have been working on. Next slide, please. For climate change information, we've went to the Palestinian Environment Quality Authority, which produced the NAP, the National Adaptation Plan on Climate Change, following the UNFCCC guidelines. And they predicted for the pathway of RCP 2.6 and RCP 6.0 on 3 different time scales: 2025, 2055, and 2090, different shifts in temperature and precipitation, which were the main 2 variables that we need to work on, because for most of the other variables that climate change would impact, or obviously there are quite a few other variables, they were completely insignificant for our assessment. So we focused on temperature and precipitation. Those predictions were basically based on the 5th assessment report of the IPCC. And yeah, that was most recent until the moment, I guess. And they used the self-organizing simulation technique in order to do those predictions. We took them as they are because of the credibility of this source. Next slide, please. For the out of all of the assessment done, because each of the variable within the water use system, whether it was abstraction from the aquifer, whether it was precipitation, evapotranspiration, specifically evapotranspiration because it's an agricultural use system, there were tremendous efforts in data collection. And one of our key findings, for instance, on the quantity part, that there's no way what's being officially reported by most of the credible resources that would meet the actual evapotranspiration demand. We've compared between the Palestinian official records and also the Palestinian Statistical Bureau of Statistics, the Central Bureau of Statistics, on their records for agriculture. And we could find that for that level of agricultural yield, you can never get that production with this reported number of abstractions. Hence, we needed to increase or adjust our abstraction recordings. Next slide, please. After that, we also adjusted the evapotranspiration changes based on the 6 different scenarios. Precipitation changes based on the 6 different scenarios, and we've run into the sufficiency equation on the meso level. And two really remarkable findings we could find there. That seemed to be that all of the numbers are above 84%, which means apparently that the system is working fine in terms of its impact on the system, on the main source, but that doesn't really reflect reality. And here there could be 2 explanations. Either you know, in a shortage mode, you always run a high level of performance because you have no other options. The second option could be there is something missing in terms of water balance. There are more abstractions that are being wasted in terms of return flow to the waste system. Those bits would require much more accountability in terms of recording of abstractions, because we've noticed that the number of unreported abstractions is quite significant in that region. And also it means higher and much more oversight of the entire process, whether it was from the Palestinian Water Authority, from Palestinian Ministry of Agriculture, or even on the political dimension, because I haven't mentioned the Israeli side thus far, and also could be within the political negotiations. The other remarkable finding that if you can see on the 6 different scenarios, almost efficiency doesn't really change, because we're assessing here at the meso level, the impact of the system itself on the water resource. We're not mentioning the macro level yet, and that would become probably the major impact. And this is because eventually, and every time the evapotranspiration increases, and every time the precipitation decreases, we would need to abstract more volume, and that would impactly balance the efficiency percentage at the end of the day. Next slide, please. Those are basically the inflow model, because the previous slide was about the consumptive model. Same results, same findings, nothing really different. Next slide, please. But here's the bigger picture, and that's what we really need to focus on. If you look into the light blue line at the bottom, that's precipitation expected decrease according to the different scenarios in RCP 2.6 and RCP 6.0. But when it comes, the same thing also for evapotranspiration, yellow line in the middle, there's only a slight increase because of the temperature increase, slight temperature increase. That would need, in the most optimistic scenario, 2.6, would at least require 19% of abstraction increases in order to meet the same agricultural demand. And here we're talking about food supplies. We're talking about much more serious topics when it comes to efficiency. And that would have to be maintained. Although we need to keep in mind population as well. Population increase and the demographics changes on that region. We haven't considered that in our analysis. On the less optimistic and more realistic side, we could reach up to 30% increase in abstractions, which is pretty damaging, unless if we can consider that on a much macro level. Next slide, please. And that's one of our main conclusions, that we can only ensure sustainability of the aquifer if it was transboundary efforts on both sides, Israel and Palestine, even Jordan's side, because it has a little bit of interest in that region. Meso sufficiency analysis is pretty important, because it highlights the weak points and the strong points of your system. We could find lots of weak points in our system, and in addition to some strong points in our system. That's what need always for the decision maker to be considered. And we offered our results also to the Palestinian Water Authority. We thank them for their high level of cooperation and providing even lots of time on the interviews. They welcomed the results, and I hope to see more efficiency consideration in their assessment for the future. Thank you very much for listening. Looking forward for your question, everyone.
Nasser, thank you very much. Very clear presentation, and by keeping under time, we can probably take a question right now. I'll have a quick look on the QA. There wasn't a specific question. Oh, yes. Yeah, related to a question by Sumanta Bazik, I also had a similar question. You reflected on the consequences, and the interesting thing, you were talking about a non-linearity here between, obviously, you've assessed an increase in evapotranspirative demand and having a disproportionate impact on the supply side, on the need for water. Perhaps if you could just respond to that, what are the consequences physically and politically, perhaps, with this increasing demand? And then a second question, if you could follow on with that, would be, what about a supply side changes? Are there ways of potentially improving either efficiencies from a strict irrigation efficiency, or some other sort of not just supply side questions? Is there a demand side where we can look at possibilities of reduced water use or reduced drought per crop?
Yep, very, very interesting questions. I would start with the second one and then jump into the first one as a consequence. So most of the Palestinian official efforts, along with the negotiations with the Israeli side, is basically concentrated on this supply side finding other ways of supply. For instance, desalination have been a hot topic for the past 10 years at least, probably more, 15. Same thing for reclaiming wastewater and find other creative solutions, let's say, for wastewater management. That is heavily dependent on the political process, heavily dependent on the donor readiness in order to finance most of those projects, especially in Gaza Strip, where most of the hiccups and ups and downs politically are happening. So most of the efforts, just to wrap it up and quickly answer your question, most of the efforts are concentrated on supply side. And you can find lots of literature within the official records about supply enhancement or at least reallocation where more needs are to be addressed. And that's what it comes also to demand management, reallocation mainly. But I wouldn't say the demand management is worked on very well within the Palestinian concept. And I think this is quite important as part of an integrated water resources management.
I imagine very quickly it has something to do with trust, because if you use less water, your neighbor's going to then take up the bit that you didn't use.
Absolutely, that was the jump exactly to your first question. When it comes to allocating, what they call allocation, each side would agree on an allocation, and you don't really need to spend much effort to go to the website of the Palestinian Water Authority just to see a claim that the Israelis are abstracting 100 million cubic meter per year more than agreed on the Eastern Aquifer Basin. Trust. Thank you very much for mentioning that word. Trust is a key in this painful process. And there is the joint committee, which is for water, which is basically joint water committee, they call GWC. They supposedly meet every now and then just to agree on the common understandings of abstraction levels and controlling the process. And that I can comfortably say that doesn't really go very well.
Thank you, Nasser. We'll move to the next speaker now, and I'm sure we'll follow some of this up in the plenary. Sara, could you introduce the next speaker, please?
Thank you, Richard. Our next speaker is David Macdonald. He's a senior hydrogeologist in the British Geological Survey, and he's going to talk about the tools to reconstruct past and project future groundwater levels to inform groundwater resource management in the sub-Saharan Africa.
Yeah, good morning. So yeah, I'm going to talk about a study that we've undertaken to use models to reconstruct past and project future groundwater levels, specifically in Burkina Faso and in Ghana. This work was undertaken as part of the UPGROW program, which is a UK program entitled Unlocking the Potential of Groundwater for the Poor. Those authors involved and many more, and there are many more are listed above. Next slide. The development of groundwater is seen across sub-Saharan Africa as an important means to support the adaptation to climate change. And there is a need when it comes to water resource management for tools that will quantify what the likely impact of climate change is on groundwater resources. And within that, understanding the current groundwater resource status in relation to the recent past is important, especially then to understand what the likely impact might be of future changes due to climate change. Next slide. There is a limited understanding, particularly of the more heterogeneous weathered basement aquifers that occur under much of sub-Saharan Africa, and also a lack of data, which means that the use of complex distributed models that might be used in other parts of the world is problematic. And so within this study, we were looking at the potential application of a more simple lumped parameter model that links together a number of simplistic conceptual models of the soil zone, the unsaturated zone, and the saturated zone, and uses that to simulate the water level at a particular borehole, but then makes some assumptions about the representativity of that borehole for the wider aquifer. And this has been used extensively in the UK to forecast groundwater levels at specific sites. So the advantage of the lump parameter model, it has relatively small input data requirements. it is driven by climate data, precipitation, and ET. And then it also uses as input observed groundwater level data for an individual borehole. And it has a limited number of input parameters, and the user provides a range of those parameters. And because the model runs so quickly, you can run it many times, millions of times if you like, to try and explore the parameter space and identify the sort of the optimum sets of parameters that can be used to best simulate the observed groundwater levels. And once you've got this model for your site, then you can use past observed climate data to reconstruct groundwater levels, but also use climate model outputs to project groundwater levels into the future. Next slide. So as I say, we apply the modeling technique in Burkina Faso, working with the Department of Water Resources there. Burkina Faso is underlain primarily by weathered crystalline basement aquifers. But Burkina Faso has an excellent groundwater level monitoring network, potentially one of the best across the whole of Africa. It has over 50 sites where it has data dating back at least 15 to 20 years, but in some cases, as you'll see on the left-hand side of the screen, right back to the early 90s, and in one case, back to the late 1970s. So we use these boreholes to develop a series of models that we then use to reconstruct and project groundwater levels. Next slide. On the right-hand side of the screen, on the right-hand side of the graph, you can see the black circles. These are the observations from a specific site in Ouagadougou. If we just think initially about the observed data across the whole of Burkina Faso, it falls roughly into three groups. There's a relatively small group where you see long-term declines in groundwater levels, and we think this is most likely to be due to over-abstraction in the locality. But the others fall into two groups, which would appear to be controlled by the hydrogeology. Short-term fluctuations, those are annual and multi-annual, or fluctuations of a few years, but also those that show longer-term changes, which reflect the longer-term patterns in the climate that's seen across much of Western Africa. So, as I say, we use these observed data along with the model, produced calibrations, which were generally of good quality, and then took climate data that was available. And in the case of Ouagadougou, this was back to 1900. And we were able to reconstruct using the models the simulated groundwater levels back to the start of the 20th century. And what we can see from this is that the groundwater levels that we saw in the 80s and 90s and in the 2000s may have perhaps not been seen previously prior to had only been seen as far back as the sort of the beginning of the 20th century. And what we saw were quite large multi-decadal patterns in the groundwater levels, as I say, sort of similar to the climate, and ranges there of about 6 meters between the highest groundwater level and the lowest. Next slide. So these models we developed, we then used them to look into the future, and we used a suite of 29 CMIT-5 models, and then looked at the 2050s and the 2080s. And we saw variability across the country. We saw in the more arid regions quite a range of outcomes in terms of the changes in groundwater level compared to current levels. And the graph at the top right there is showing the change between current groundwater levels and an average for the 2050s, and the number of CMIT 5 models, that's the y-axis, the number of models that showed changes in the ranges that are shown on the x-axis. And what we can see is there is a very wide variability, a wide range in in the changes in groundwater level that are projected, which shows the uncertainty of using climate models, and particularly this is the case in the more arid regions of the country. But what we can see is that most of the models are agreeing on a change in groundwater between 0 and 5 meters, and in fact the median there is about 1.5 meters. We compare that to the southwest of the country, and that's the graph on the bottom left. And here the range is much smaller. It's between an increase of 3 meters and a decrease of 3 meters in groundwater levels at this particular site. But most of the models are clustering in around 0, so from -1 to 1. So we're seeing changes perhaps projected using the model that are well, we can compare those projected changes to the reconstructed changes. Admittedly, both are modeled responses, but we are perhaps seeing more of a change associated with those climate patterns that people have been researching over the past decades, compared with the changes that we might see due to climate change. The last slide, please. So finally, just in terms of insights and implications, so we are seeing differences in groundwater level responses due to climate variability, but also due to hydrogeology. And what we see is that potentially reconstructions show us that the responses that we've seen in groundwater levels due to these multi-decadal climate variabilities that we see over past many decades may actually be relatively small in comparison.
Sorry to interrupt, David. Can you wrap it up in a minute, please?
Yes. And that's it, really. So, and the last point I wanted to make was the importance of long-term monitoring, and that the Burkina Faso government should be commended for the work that they've done maintaining that monitoring network across the country. Thank you.
Thanks, David. Thanks. I think we have run to the time, but maybe we'll do one quick question right now. In the scenarios that you developed, what about these were, I presume, when you did the climate change scenarios, these were assuming pumpage, contemporary pumpage remains the same, is that it? Or did you build in a kind of pumping scenario or change in use?
Yeah, I mean, perhaps I didn't dwell on the assumptions enough of the models, but okay. There are assumptions made about the land use staying as it is, but also that there was no abstraction. So assuming that these boreholes were located to be as far away as possible from the influence of any abstraction, we saw that wasn't the case in all of them, but there is the potential to build in abstractions into the modeling, but yeah, that is an assumption at the moment, that we don't see the influence of abstraction.
Okay, thank you, David. We'll take up more in the plenary. And Sara, could you please introduce the next speaker?
Okay, this is our last presenter today, and he is Abdul Qadir Larabi. He is a professor of water resource modeling in the University of Muhammad Hamza, I guess. That's 5, it says in English, but I guess it's in Arabic, it would be Muhammad Hamza in Rabat, if I'm correct. Please correct me, Larabi. So he is from Morocco. He's going to present his presentation on the assessment of climate change impacts on groundwater resources using record data and in the Beni Amir Aquifer in the Morocco.
Just to correct Sara for a moment, it's the last presenter in this session under theme 1. There are further presentations after this particular session. Okay, please go ahead.
So thank you, Sara and Richard. First, I would like to thank my colleagues, Dr. Marlene and Dr. Ziad Khayat from the UN Economical and Social Commission for the Western Asia for their contribution and also for their support to this project in Morocco. So this project consists on the assessment of climate change impact on groundwater resources using the RICARD data. This RICARD is an initiative, regional initiative in the Arab region. So it was a large study, and we have some results. And these results, the output of this RICARD was applied here in Morocco to see what can give at the end. So next, please. So the objective of the study is to assess this climate change impact on groundwater resources availability and use in Morocco, and specifically in this case study. So the case study, as you know, is located in between the high central Atlas, the mountains, and the south and the phosphate highlands in the north of Morocco, generally in the center of Morocco. So the area covers an important agricultural area that produces beet cultures to supply 3 important sugar industrial units in Morocco, in addition to supply drinking water of several urban centers of the area of the industrial water supply of OCP is the phosphate for the process of washing beside the water requirement of the agriculture of the large irrigated area. Next, please. Again. So the key issue and the problems addressed behind is that the regional initiative for the assessment of climate change impacts on the water resources and socio-economic vulnerability in the Arab region has shown that the Arab region will experience rising temperature and largely decreasing precipitation. And more specifically, precipitation trends will be largely decreasing across the Arab region through the mid-century. As well as Morocco belongs to this Arab region, so the groundwater resources will be affected by climate change due to the reduction of natural recharge, which comes from the reduction of the precipitation and the increase also of the evapotranspiration. So the issues is how groundwater availability will vary under this climate change in this region. And also, can we extend irrigated area, especially sectors based on groundwater supply? And also, what are the best management scheme of groundwater? This is what we are looking for. Next, please. So the methodology, the coupling climate and hydrological modeling, and using the 2 scenarios, RCP 4.5 and RCP 8.5, as it was selected from the RICAR initiative. So it's to draw the RICAR and the output of the 3 RICAR initiatives, and also the 3-dimensional model for groundwater flow has been developed for the area, and in order to account for the effect of climate change on this aquifer, and using the 2 scenarios. Next, please. So for this, to do that, a hydrogeological database was developed, and this database really, it includes a lot of data, and including the RICAR data for climate change, and especially for the future from until 2100. And as you can see, here there are some tables and also some thematic maps that we could draw from this hydrogeological database. Next, please. So this is the results from the RICAR outputs. As we can see here, precipitation are decreasing, the trends for both scenarios, and also the temperature is increasing for the 3 selected regional models that we have selected. And we can see also that we calculated the recharge, the groundwater recharge, and we can see due to this reduction in precipitation and the increase in evapotranspiration, this recharge is really decreasing. Next, please. So we simulated this impact of climate change and for the 3 climate models, and we can see already in terms of water balance model, we can see that for the RCP 8.5, really the water balance is decreasing and decreasing, and the situation is severe, while for the RCP 4.5, the situation is less severe, and this is reflected really for the drawdowns variation for the whole period from 2020 to 2001, and we can see on the right that there is decrease of the drawdowns in the aquifers. Next, please. So the result of the average of the 3 climate model, we can see already that we have the decrease for the drawdowns for the observations well, which are installed in the area. And we can see that also in terms of storage and of the storage, the aquifer really is the storing water. So we are not gaining much in this climate change impact. Next, please. So in terms of water balance, and we can see that we can divide the result in 2 periods. So one period from 2020 until the mid-century, where we have really less water, less storage, and for RCP 4.5, and we have a severe situation which is decreasing and decreasing for the second scenario, and the minimum of the water balance is for RCP is 140 millions, while for the RCP 8.5 it will decrease to 120 million cubic meters. So next, please. Okay, so as a result of this situation, we see already that some area will be completely dried, especially for the RCP 8.5, and you can see already on the left, the second figure, that a large area will be dried, and the wells will be dried there, and will be abandoned completely from the irrigation, while for RCP 4.5, the area is a little bit reduced. So this is really a catastrophic situation for the irrigation in the area. Next, please. So as a result for this presentation, we can conclude that groundwater resources in this aquifer will be affected by climate change due to reduction in natural recharge from reduced precipitation. The mean will be 20% less at the end of the century for RCP 4.5 and 50% less for RCP 8.5. So the increase in evapotranspiration caused in part by higher temperature. So the mean will be 2 degrees increase for RCP 4.5 and 4 degrees increase for RCP 8.5 at the end of the century. While for the availability, for the water availability in the aquifer will decrease for both scenarios, showing a severe situation for RCP 8.5 scenario. This will result really in groundwater table decrease for both scenarios, varying from 10 meters for RCP 4.5 and to 25 meters for RCP 8.5, which makes some aquifers area completely dry. So finally, the results are of great importance as a key information for the decision makers regarding the future for the systemic exploitation of groundwater resources in the aquifer. So the result for the RCP 8.5 present a great concern for the future irrigation in the area. So as a recommendation, so the adapted measure that accounts for this impact of climate change really specifically in improving productivity in the agriculture sector, which are urgently needed, such as extensive recognition of gravity irrigation to drip irrigation and adapted crops that are water efficiency and more resilient to climate change. And we need also to generalize the assess of impact of climate change for the other groundwater aquifers to underline the consequences for the entire region and seek for operational measures for the adaptation and management of groundwater system in an adaptive and optimal manner. So thank you for your attention.
Yeah, thank you, Professor Larabi, for your presentation. We can see that the projections are rather stark and as you said, rather serious. And one part of the analysis I was just wondering whether you might comment on is, in dryland environments, we know that there's often a kind of episodic nature in which replenishment occurs, natural recharge occurs. So some years where it is particularly heavy rainfalls that may be providing a substantial amount of the recharge. One thing I didn't quite get from your presentation from the historical record is the extent to which your analysis accounts for this type of behavior, or the roles of climate extremes in providing episodic recharge. Is that something that you observe in Morocco?
Yes, this is a very good question, because for the extreme events, they are very important and they are very frequent in Morocco. And the problem is that sometimes this inundations or this floods can go directly to the sea, and we need really to retain this floods in order to improve the groundwater recharge. You are right in your comments, because this is very important, as the groundwater aquifer recharge is also coming from the surface irrigation, because we are irrigating and in the same time we are recharging the aquifer. We are also pumping, so both recharge are occurring in there. So they are recharged from surface water, and also the recharge also from natural precipitation.
Great, thanks very much for your response. We now move into this session. We now move into the plenary session, in which we'll review some of the questions that we've heard from the audience. I'll begin by fielding a couple of questions that were for John Mackay in the first presentation. And there were some interesting bits, Jonathan, in your presentation, where you talked about the contribution of groundwater discharge to the meltwater flows. And I suppose we had a question from the audience, from Bilgun, around how representative, or what are the implications of your findings in Iceland? How might these also relate to other glacier systems, perhaps in Central Asia, and the possible either misrepresentation of meltwater flows, or even just the calculation of meltwater flows? Jonathan, could you respond to that?
Yeah, sure. So, yeah, a very good question, and one that I'm keen to answer as well. But yeah, as I mentioned at the start of the presentation, these systems are very poorly studied. They're rarely studied, to be honest, and our work is quite unique in that respect. So how representative is our study in Iceland to, say, a region?
Or I guess maybe I'll put it more directly. So the findings that you made, where you found the diffuse recharge and then the groundwater discharge contributing to the meltwater flows, might these sort of dynamics also be occurring in areas in Central Asia?
Yeah, so yes, they will be. I would suspect, but no, they aren't similar systems. So I mean, just if you think of the climate regime, for example, in Central Asia, we can have quite an arid system, whereas we were working in a very temperate region, so lots of rainfall all through the year. So we would expect, so we found groundwater contributes about 15% of the total runoff in our system. In Central Asia, where it's more arid, you would suspect, well, it depends a lot on scale as well. So it depends on where you're looking in the system.
That was a kind of an interesting bit about the area that would enable diffuse recharge to take place. That would also act as a constraint. But I suppose these dynamics are things that probably are underappreciated and maybe need closer scrutiny in these systems as well.
Yeah, exactly.
Okay. We'll maybe move to one other. In your work, there was a question from Tibor Stigdor about your use it looks like very prudent use of clustering. You know, when you rather than running some massive number of scenarios, you first cluster them. And his quick question was, how well do you think the 5 that you resolved on represented the spread or range of variability in the projections?
Yeah, so I've actually just been typing out an answer to this.
Okay.
A really good question, and yeah, of course, so how do we select them? So we select them based on, we use a series of signatures, what we call glacier-hydrological signatures. So things like glacier extent, river flow, precipitation, temperature. So we looked at all these different characteristics. We had 11 different signatures. We found that those 5 scenarios that we selected covered on average about 61% of those different signatures. So we're relatively happy that the characteristics we were interested in are covered reasonably well. So say 60%-ish, let's say. We chose the cluster analysis approach. We wanted a small number of scenarios. And the reason for that is because we're looking at a very complex system. We're looking at this cascade of water flow all the way from the climate through the glacier to the groundwater system. And we really wanted to take a very process-based analysis. So we wanted to look at all the intricate details. It's very difficult to do. You're averaging your over large on some. So that's why we chose the cluster analysis approach. So to answer your question, we're happy that it does cover those ranges to some extent, but it is limited, and yeah, we chose that approach for those reasons.
Thank you, Jonathan, for your full reply. Well, we have a question now for Alan, and I guess maybe Alan, I asked you before when we left your presentation, if you could join the dots in your conceptual model of the linkages between this climate variability and the malnutrition. I guess could you now respond to that?
Yeah. First, I think I had a question from Tibor that I already answered in the chat, so we can go back next if you want. And concerning your question, Richard, well, there is joining the dots in the conceptual framework of this linking climate variability and malnutrition. Well, as we know, there's already a conceptual framework for malnutrition given by the UNICEF and many other actors. However, when we look at what it has been done for malnutrition specifically, well, we can see that climate variability will impact different diseases, not only malnutrition, through different pathways. It's not that we are telling that there is a direct pathway from the climate to the disease itself, but that it's going to go through different factors. For example, the groundwater resources in Madagascar, for example, will affect how they produce the agricultural system. They will also affect the wash services that are available. And this is a very important thing because we are talking about climate variability and how it will impact the water resources. And at this time, the water resources will impact in different other factors, such as the wash services, etc. So it's a very complicated concept.
So I suppose you're saying it's not only about, conceptually, it's not only about producing food. If you're deteriorating water quality, then people are suffering from diarrheal diseases, it's also the absorption of that food that would also be impacted. So there's multiple ways in which the water resources are then impacting this factor. Is that the point you're?
Yes, and what I mentioned to Tibor, for example, is that we want to characterize the direct and indirect associations, but we also want to identify which would be the best indicator that can help us to predict the increases or the decreases in the health indicators.
I think Tibor had another good question in which he asked, when you are looking at your relatively short period of observations, we realize we have to work with the data that we have. but it was, to what extent might this be representing a proxy for how things will happen under climate change? Do you have maybe a response to that?
Yes, so far we haven't assessed the picture itself, but also it's not, it's only the first stage. We are focused in the district of BUET, but we are also gathering data for the other 8 districts from 2014 and now till 2020, because we have the climatic stations in southern Madagascar. So this is the first stage only to assess the associations. But we will keep the surveillance for further, like for the next years also. And what we are trying to do is implement the early warning system from these indicators.
We also had a question for David from the audience. Yeah, I suppose it's partly been answered, and so David, I don't know if you have anything further to add around the assumptions, further assumptions that are built into the, if you want to call it training set that you do over the period of observation and then extend. Can you just confirm maybe again that these assume essentially no change in land use and no change in pumpage?
That's correct. Yeah, I mean, I think this is a kind of a starting point, and there's potential to make the models kind of incorporate some of these other aspects. I used the point was made in the question about the use of Ouagadougou, and yes, you know, recognize that that's not the best example in terms of a site that doesn't have the influence of change in land use and other abstractions. And I mean, you've worked on that data set yourself, and you're trying to kind of understand the implications of nearby dams, etc. I suppose I used the Ouagadougou case there because it's a good set of observation, and also there's a good set of climate data. But yes, perhaps it's, you know, the approach in the form is at the minute, it's probably one of the sites where it's of less, you know, where the assumptions are at the greatest. So
I can tell you it still remains challenging, even knowing that site quite well, in that, yeah, what are the influences of surface waters, in this case, these barrages that are within Ouagadougou? We could think of that more broadly across not only Burkina Faso, but in other drylands. What are the influences that may be occurring more locally from ephemeral ponds or ephemeral streams versus a more wider diffuse signal? I think that's one of the big challenges in trying to resolve the data from that.
Well,
so,
what the model does pick up are those kind of longer term variations in groundwater level. It might not be able to pick up quite the absolute values of the lows, but it does pick up those kind of decadal changes.
Great, thank you very much, David. We'll perhaps leave the last word perhaps back with Nasser. Nasser, there was a question in the boxes asking you about efficiencies, and maybe that's going back to our earlier discussion. And I think there was some curiosity in the analysis you did more generally. We don't have time to have you explain all of that, but I suppose, is it as simple as I was making out, or I'm sure there's more interesting detail here that although of course there's competing uses and overuses, and we won't necessarily, well, we know where those are occurring. Do you have any hopeful suggestions of how it isn't a race to the bottom, meaning that, that I guess it is built on trust, where improved irrigation efficiencies on both sides may lead to an improved resilience in the water resources themselves. But do you have anything to add to this?
Yeah, we've got one publication I can also share it on the written answer later on. We've run 4 different scenarios apart from climate change about what we can do in terms of practices, 4 different practices. 2 of them excelled among those 4 options. The first one was to improve the selection of more socioeconomic benefits in terms of selection of food products. And the second option was also to enhance water reuse within agriculture. Those were the 2 more practices that enhanced efficiency the most. But I will share the publication later on. Thank you. Prof.
Thanks very much, Nasser. We need to wrap up this session now. Thanks to everybody for all of your contributions. Fantastic. Well done. And also thank you very much to my co-chair, Sara and Nowreen, for doing an excellent job. Okay. Bye for now.
Bye-bye.
Bye-bye.
Thank you.
Thanks.